We got it to work. I would like to answer your questions, so let me get some space over here. Yeah, this way we can have today be going over hopefully 2 sections if I can, and then Wednesday a section in review and Friday a section in review. I mean Friday just all review. Plan on going through 2.8 and 2.9 today, or 2.7 and 2.8. I plan on going through 2.7 and 2.8, and then we'd only have 2.9 to cover. So I may just like record that and have Wednesday and Friday be review sessions. Okay. What is your question, sir?
So I'm like on that. I forgot what you need to find, but look, I'm just gonna show you like how it's like the thing. So it says f of x.
Make sure I don't walk right off the board here. What does it say?
So f of x equals sine of x. Comma.
And what?
Comma.
Comma.
Yeah, and then it's like f. Just write like the f, and then raised to the like 4,000 power.
Uh-huh.
Of x.
Uh-huh. Does this really mean f raised to the 4,000th power of x?
I don't know that.
No, it doesn't.
I don't know.
I got you. So dx of f of x can be written as f prime of x. Then the x of f prime of x can be written as f double prime of x. Or you could say that this is equal to d squared dx squared of f of x. So the more number of primes you have, the more number of derivatives you're required to take. Now, mathematicians, after 4 primes, we just kind of skip to just now saying, okay, or this just means take the 2,000th derivative. What is the 2,000th? Once you take 2,000 derivatives, what should you get? Once you take 6 derivatives, what should you get? Once you get 5 derivatives, what should you get? So if f of x is equal to sine of x, what is f prime of x? The derivative of sine is what?
Cosine.
You guys need to know why. You guys need to know that derivative of sine is cosine, and you guys need to know why. Okay. Okay, so that's cosine. But then what's f double prime of x?
I think it's negative sine.
Yeah, f double prime of x is the derivative of this twice. So the derivative of this once is cosine, and then derivative of this is what? Negative sine?
Mm-hmm.
Yeah, you're right. You guys know that it's negative sine? You need to know that. That's in the previous sections. Okay? There's a lot of catching up to do. All right? So then I asked you, what is f of 4,000? Or what is the 4,000th derivative?
How do we solve that?
Huh?
How do we solve that?
Oh, how do you solve that? Oh, that's what you're asking, is how do you solve that?
Yeah.
Oh, it's actually not as hard as you think. Let's continue. What is d cubed dx cubed of f of x? This is f triple prime of x. But that's just simply d dx of negative sine of x, right? But what is that? Derivative of sine is what?
Of sine?
Derivative of sine is?
Oh, so that's cosine.
So then you just put a negative on it.
Yeah. Cosine?
Yeah. So then, what is d to the 4th dx to the 4th of f of x? This is the same thing as f 1, 2, 3 quadruple prime of x. But that's the same thing as dx of negative cosine of x, which is equal to what?
Negative sign, so it would be positive sign.
Yeah, what's the derivative of sine? What's the derivative of cosine?
Negative sign.
The derivative of cosine is negative sine. So negative of a negative sign is a positive sign. No pun intended. So let's look at a pattern. Let's take one more derivative. We're going to find a pattern. What is f? 5 derivative of x. That's d dx of sine of x. What's the derivative of sine of x?
Cosine.
Cosine of x. But have you noticed that we've actually gotten that before as a result? So they repeat, don't they? They have some type of pattern to them. So we take the derivative of sine, it becomes cosine. Then we take a derivative again, it becomes negative sine. Then we take a derivative again, it becomes negative cosine. And then we take the derivative again, it becomes sine. And then we take the derivative again, and it becomes cosine. It seems like, look, this pattern repeats. If we take the derivative of this again, what's the derivative of cosine? Negative sine. So it's going to repeat the pattern. So what is the 4,000th derivative of sine of x?
I don't think I need to count them till I get to 4,000.
No, you don't.
All right. So
Which one of these powers, 1, 2, 3, 4, do you think it should be?
probably 4.
Yes, because 4 is a multiple of 4,000. 4,000 is a multiple of 4. That's what I'm trying to say. 4 is not a multiple of 4,000. Does that make sense? Yeah, so like, well, yeah, take this derivative 1,000 times. It adds up to the 4,000th derivative. And you know what you get. Every 4 derivatives, the sine of x repeats itself to the value sine of x.
Right.
Yeah.
So if it was like 2,000, then it would
To
be
what?
for the 2,000.
2,000?
Then it would be for the second one.
Yeah.
So it would be negative sign.
Yeah.
Right?
Yeah.
And stuff like that.
Mm-hmm.
I think I get.
Okay. In math, it's important to look at patterns. But to do so, you have to have like the capabilities of taking these derivatives. And not only that, the ability to stay focused. That's why I'm like, put away your phones, put away your social media, stop being on your phones all the time, stay focused. Train your brains to have higher levels of focus. Your brain's just capable of way more than you think. Way more than you think. All right, what's the other question?
Oh yeah. So there was this. So you're given like f of x, right? And then you need to draw f prime of x.
Oh yeah.
But I got like confused. I didn't know how to draw them.
What does f prime of x tell you?
The derivative?
What does the derivative represent?
I think like the zeros.
No.
No?
No. No.
X equals 0? No.
No. So here's our f of x.
Tangent line.
Yeah, kind. It's related to that. Let's say here's our f of x. Here's our f prime of x. How do we know it? It relates to tangent lines, yeah? So over here, notice that the tangent lines are positive. 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 And then they become 0 here. At this point right here. So we could say, you know, at the similar point right here, let's say this is -1. The derivative graph, fine. It's going to be positive valued, but dipping towards getting 0. Here it's positive, 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 but then it decides to be 0 here. Because the slope of the tangent line decides to be 0 here. And the derivative represents the slope of the tangent line. It's the rate of change of the function. So over here, if this is like a 5, then f of -1 is equal to what? But f prime of -1 equals what? Very good. Very, very good. Yes. Because this function is telling you what is the slope at the various points of the function. This function is telling you what is the value of the function at the various points of the function. They're two different things, but they're related. So then after it becomes 0, it starts to dip into the negatives again. Negatives, becomes 0 again. So let's represent that here. It goes through a period of negativity. I'll say here at like +5, but then it's eventually going to turn a positive characteristic there, past, let's say 5. So here, we'd say, okay, the slope becomes 0 at -1, and it's negative all the way up to like 5 here. And then it assumes positive values. That's that. I won't like, you know, if I draw it like this, but you draw it like this, I wouldn't be mad. Well, don't draw it like that because it seems like it's asymptotically approaching a certain value, and that's not necessarily true. But what I'm trying to say is like, your drawings shouldn't be perfect. You don't draw. I don't expect your drawing to be perfect. What I expect is, okay, given a function, did you represent it had a negative, positive slope from negative infinity to -1? Did you indicate that it had a positive slope? Then at -1, did you indicate that its slope became value 0? Then between -1 and +5, did you indicate that it had a negative value for its slopes? And then did you indicate that there was a shift at +5 to positive values of slopes? That's all I care about.
Okay, so what I get is that whenever like it's going up, so like positive, it needs to stay on y equals like positive numbers, right? And whenever it goes down, it becomes negative, like it needs to be y.
Has nothing to do with the y equals.
No, what? Because you see how like you have like the graph, right?
Oh, are you talking about f prime of x?
Yeah, because like whenever
Okay.
you compare,
Yes,
right?
that is right.
So like whenever like the slope over here is positive, right?
Yes.
It needs to be on y equals positive, right?
Yes.
And then whenever it goes down and it's negative, it
Yes.
needs to be on y equals negative.
For the derivative, we could have had the normal function. If I drew a function like this, let's see, let's have it. Yeah. I could have drawn it like this right here. And it would have had the same derivative graph. But look, this is above the x-axis. That's below the x-axis. That's what I was trying to say.
Yeah.
For f of x, it doesn't. You know, for f of x, it doesn't matter where it's at.
Yeah.
But f prime of x, it does. Yes.
So you're saying that you can have like the same derivative even though it's not the same graph. Right?
Yeah, because look, positive, 0 at -1. So it'd be just like that. Then it becomes negative, 0, not positive, but 0 at 5. Boom, like that, negative, 0 at 5. And then it decides to become positive positive beyond that, and so that represents that. So both those functions have the same derivative graphs. So it doesn't matter. Yeah. Yeah, okay. I don't think I need to say anymore. Any other questions? I don't mind not getting through what I'm planning today if you guys are just, because answering your questions early will allow you to like digest and understand it for later. So I don't mind if you want to make today a review session. As long as you have questions, I'm going to give you answers. If we don't get through the material, I'll just like upload the lectures. That's the least I can do for abandoning you guys for how long? 2 weeks? Yeah. I didn't really abandon you. Physically, I did. What else?
For those, at least for now, I'm still missing 2.5, so I'm gonna do that.
Okay. Any other questions, guys? You're Luis?
Yes.
Luis, David, and Harrison? No questions from you guys? Okay. That means you're all going to get 100 on this test, right?
No.
Well, if you don't get 100, then I'll be perplexed as to why you had no inquiries. So 2.7 rates of change. This all stems from the fact that given a position function, so let's say this is a position function with respect to time t. What do we mean by that? Let's give a simple example of, let's say we have a function like this, where f of x is equal to negative x squared, let's say, plus 10. So right here, we're at 10. Let's say such a function, for the sake of relevancy, replace the x with the t. So f of t is equal to negative t squared plus 10. Let's say that's a position function of an object falling off of a cliff. Let's say you threw a rock off of a cliff and its position with respect to time is like so. Let's say the cliff has a height of 10 feet. We say the height of the function, and instead of f of t, we could call it p of t for its position. The height of the function, p of t, or the position of the function, is p of 0. This is at time equals 0. Notice what that is equal to, negative 0 squared plus 10. So that's equal to just 10 feet. So clearly, before you drop the rock off of the 10-foot cliff, its height is the 10-foot cliff. But as time moves forward, you're going to see that its position is going to drop. What about at t equals 1? After 1 second, where's the rock at? Well, this becomes negative 1 squared plus 10. So that's negative 1 plus 10 is equal to 9. After 1 second, instead of being at 10 feet, now it's at 9 feet. Right here. So this correlates to time equals 1. Then you move on and you say, what is this position at time equals 2? Oh, well, that's just if this position function truly models the rock, then it's going to be negative 2 squared plus 10. But that's a negative 4 plus a 10, and that's a 6. So at 2, it's going to be a 6. So it's eventually going to hit the ground, right? At what time does it hit the ground? We can figure out at what time it hits the ground by saying its position or its height equals what when it hits the ground. So then you put the left-hand side equal to 0, and you equal it to the function negative t squared plus 10. And you solve for t. You find the time in which would make the position or the height equal to 0. So I add a t squared to both sides. I get t squared is equal to 10. I take a square root. I get t is equal to plus or minus square root of 10. So can there be a negative time?
No.
Yeah, in this situation, it doesn't really make a lot of sense, although that could be arguable if you look deeper into the situation. But let's say we're just like not trying to invent new theoretical physics, and we just want to deal with really straightforward things. One could argue that at every point in time, there exists wormholes, which are Einstein-Rosen bridges, which will take you into a hyperdimension and let you go backwards in time symmetrically to the equations of motion of Newtonian mechanics. But we don't want to get into all that, right, David? You don't want to get into all that? Yeah, you just want to pass your test, huh? Okay. So we'll just take this positive time right here, square root of 10. Because it doesn't make sense for the rock to hit the ground at a negative time. That means it hit the ground when you went backwards in time. It doesn't make physical sense in this classical situation. Maybe not to us right now. Maybe not to mere mortals. Yes.
But wouldn't it have to be the positive one too because of the graph?
Yes, that's right. That's exactly right. You pick the positive value because the graph, this is with respect to time, and this is with respect to height, let's say in feet. Yeah. People who talk about parallel universes would say, oh, but in a parallel universe, the same thing happened going backwards in time. And that's where the other solution exists. But that's not going to be on your test. Thankfully, man.
It messes with my brain and stuff.
But that's cool. Things that mess with your brain are cool. Why? Do you just want to sit there and, never question things? Oh, you.
I mean, I guess you're right on that. But I'm still trying to figure out the other 2 points.
Other what?
The other section.
Oh, yeah, that's fine.
But I mean, later on, maybe.
Mm-hmm. Right. Okay. So that's the idea behind an equation of motion, all right? You got a function, you plug in time values, and it'll tell you a position, right? So this is a position function P of t. What happens when we take the derivative of a position function with respect to time, d dt of P of t? It becomes a P prime of t, right? What does this represent? If this represents position,
Whenever there's no change. No?
this represents position. P of t is position. So its units are in distance. Right? I am 3 meters away from you, 4 meters away from you, 2 meters away from you. This is my position function with respect to you guys. What is the rate of change of position? Speed, distance over time, or velocity. Speed is just purely the number. Velocity is the number with a direction associated to it. So speed is 100 miles an hour. Velocity is 100 miles an hour due south. Right? Associated with where are you going? 100 miles an hour is your speed. Where are you going is 100 miles per hour east. Oh, now I get that your speed is now in this direction. That becomes a velocity. That's the difference between velocity and speed. Speed is just the number. Velocity is the number with the direction in which that speed is going. And this is what this is. And this is distance per unit of time. So an example of this is miles, meters, feet. An example of this is miles per hour, meters per second. So then what's d dt of v of t? I'll give you the easy one. It's v prime of t, right? But what's that equal to? You guys ever been inside of a car that's moving constantly at like 60 miles per hour? Do you feel like the car is like really like doing anything? It feels like you're sitting still, right? If the roads are perfect, there's no bumps, you're not switching lanes, it just feels like you're sitting still, right? But what if then out of nowhere you hit the gas and you move up to 90 miles per hour and then you decide to be constant? In that stage between 60 miles and 90 miles, you felt something, right? What was that thing that you felt? A change in velocity or speed, yes. And what is a change in velocity or speed called? A rate of change in velocity is called what? We have a word for it. Acceleration. So we'll call this A of t. Equals acceleration. Acceleration or acceleration. I don't even know if that's an E or an A. Acceleration, maybe. Acceleration. Maybe it's acceleration. Who here is a spelling bee champion out here? I don't even know. I'm not sure how to spell acceleration. Oh, yeah, it's with the E. Yeah, it's with the E. So let's do an example. Let's say your position function is t cubed. What is your position at time equals 3? Your position at time equals 3 is p of 3, which is just 3 cubed, which is 27. Whatever it's in, meters, inches, centimeters, whatever. So what is your velocity at time equals 3? General equation for velocity would be what? 3t squared, because you take the derivative of t cubed, you get 3t squared. So v of 3 is 3 times 3 squared, which is 3 times 9, which is 27. And what about your acceleration at time equals 3? Yeah, A of t is going to be equal to 6t. So A of 3 is going to be equal to 6 times 3, which that's 18. Does that make sense? Yeah. That's how they're related. So the derivative gets you from position. Take one, it becomes velocity. Take another one, it becomes acceleration. Take another one, it becomes the jerk. The jerk is equal to the fourth derivative of the position function. So the jerk is here is equal to 6. So P of 3 is just 6 because it's all 6. P of t is equal to 6 doesn't depend on t. There's no t's in the expression. It's just a 6. So for all values of t, it's just 6. So if you're accelerating and, you know, something happens, you put on the NOS or something. Who knows what NOS is? I think every dude knows what NOS is, right? Race cars, you know, that little illegal stuff you can install in your car. You hit it, it makes you go extra fast. Nitrous oxide, N2O. Makes flames come out of your mufflers. Fast and the Furious. Yeah, let's say you're accelerating and you hit the NOS. There's going to be a jerk because there's going to be a change in the rate of your acceleration. So let's say we have a gluon. So we have a gluon in the strong nuclear force field. And let's say it has a position function inside of a nucleus of t cubed over 3 minus a t. Let's say its position is in nanometers. And t is equal to seconds. What is a nanometer compared to a meter?
I think it's like 9 times. Like more.
Yeah. Here's a 1 meter. A millimeter is, you know, it's a millimeter because 1 millimeter is equal to 10 to the negative 3 meters, right?
Yeah.
And then what? What happens when you go to millimeter? What's nanometer?
I don't remember if it's 9 or 12.
Yeah. Next comes 1 micrometer, which is 10 to the negative 6 meters. And then it becomes 1 nanometer. This is 10 to the negative 9 meters. I believe you said that. So what do we mean by 10 to the negative 9 meters? We mean it takes 1, 2, 3, 4, 5, 6, 7, 8, 9 nanometers to equal 1 meter. So over here we got a meter stick. Million, billion. So there's a billion nanometers just in this 1 meter stick. A billion nanometers. Okay. Isn't that cool? It's a very small length, a nanometer, the nanoscale. So we have a gluon. A gluon is a force-carrying gauge boson of the strong nuclear field. It's called a gluon because it's the glue that keeps the nucleus of an atom together. You guys ever wondered why does the nucleus of an atom have protons and neutrons?
Why?
Yeah.
No,
Don't you
I
learn
don't
that
know.
positive repels positive in the electromagnetic field? Positive repels positive, negative repels negative, but positive and negative attract. So how the heck is the nucleus filled with a bunch of positive charges? How come it doesn't explode, right? It's the gluon. The gluon is what's holding those together. The gluon is the force carrying particle that holds the nucleus together. Okay, so it's inside a strong nuclear force field and has a position function like so. Let's see. What do we want to ask you? What is its average velocity between t equals 0 and t equals 2? Remember, average velocity is different than instantaneous velocity. Average velocity is equal to v of 2 minus v of 0 all over 2 minus 0. Okay, so to figure out what is the average velocity, we have to know what is the velocity. And to figure out what is the velocity, we have to do what to the position function? Yeah, the derivative. So p prime of t, which is v of t, is equal to what? T squared minus 1. Why? Well, when you take the derivative of this, the derivative hits that first term, it becomes 3t squared all over 3. The derivative hits that second term, it just becomes a minus 1. The 3's cancel, so it just becomes t squared minus 1.
You don't need to do that, the other one, the
Hmm?
one where you do, because you know it's like
The chain rule?
a division.
No, because that's a constant.
The one on the bottom.
Yeah, the quotient rule would enact. The quotient rule would enact if you had something like this. This is a function of t. The number 3 is a constant. It's not a function of anything.
So like if it's like that.
Yeah, it has no variable t in it in its expression. It's just a number. Whereas the top does. So really, in this case, we're taking d dt of some c f of t, where c is a constant, and the derivative ignores constants. The derivative just ignores a constant. That constant just comes along for the ride. It differentiates the function, but it doesn't touch the constant. Now, if it was the d dt of a constant all on its own, that's a different story. That becomes what? Yes. But if it's d dt of a constant times a function, it just attacks the function and ignores the constant. But if the constant's there all alone, it's going to attack the constant and make it become a 0. Make sense? Okay. So over here, this is our velocity. So we can discover what is v of 2. And we can discover what is v of 0. So then we can put these right here. And negative minus negative is a positive. You guys know why a negative is a positive?
When negative times negative is positive.
Yeah. Okay. So I'm going to face the same way you guys are facing. Positive is like from 0, go right. Negative is like from 0, go left. When I'm positive, let's say I'm a positive 3, and you put a negative on me, and then I go all the way over here. So it means the opposite of where you're at. Negative means if you're positive, put a negative means opposite. So what is the opposite of opposite?
Oh,
So if I say, what is the opposite of my right hand?
left.
It's my left. So what is the opposite of my right hand? You have to do it step by step. Opposite of opposite. Opposite of right. Opposite of right on its own is left, right? And opposite of left is, yeah. You computer people. Does it look like a logic gate? Yeah. That's why a negative times a negative is a positive. Logically, that's what we must assert. That's a pretty quick way of explaining it. Okay, so now we found the average velocity is 2. And what are the units? 2 what? Because I will count off if you just write 2. I gave you the units. So what is the units?
Meters.
Yeah,
Oh, but divided
per
by-
second.
um,
I will count off if you don't put your units. Because I gave you the units, nanometers and seconds. Okay, but that's the average velocity. That's not the instantaneous velocity. What is the instantaneous velocity at t equals 2?
We would do the like 2 plus alpha. Or like.
We don't need to. That plus alpha was to do the derivative before we had the power rule. That was a hard way of doing it. We already did it using the easy way. So what is the instantaneous rate of change at t equals 2? What is the instantaneous rate of change of position? So what is the instantaneous velocity at time equals 2?
3.
Yes. Okay. I think I'm getting an important call here. Excuse me. Hello? Yeah, you-
That watch the videos.
Yeah, that's true. Have you watched all
I watched the 2.3 and 2.4.
of them?
Yeah. But I think for 2.1 and 2.2 I read the book.
2.3 and 2.2 in the book are so long.
Yeah, that's why I saw the 2.3 and I was like, I'm gonna just watch it.
Watch the video. Yeah, because it's long. I was like reading it, and I was like 3 pages in already. I was like, oh, how long is this? And I kept going.
Yeah.
I went on to like 10 pages.
Yeah, that's why I was like, yeah, let's just watch the video. I mean, at the same time, like, you know, the video like lasts so long, right? So you're like, the same time, it's
Really done.
like 40 minutes, and you're like, oh man, I gotta be here for 40 minutes, you know. But I'm like, nah, I guess it's better than reading the book. 'Cause, I mean, for those, you know, that are too long. So
Yeah.
I guess like I take longer reading
To read.
the book and stuff like that, and just watching the video.
What do we have for networking?
I don't know, an intro point number. I know.
Mm-hmm. We took that practical. There wasn't a discussion this week, right?
It was, I don't think so.
We probably have something to do. Whatever it is.
You know,
Because in class we took that thing on setting up a home network, right?
oh yeah.
Well, what homework did we have, do you remember?
No, I don't remember.
Did he say when the homeworks are due, Luis?
No, I thought they were, well, I did 2.3 because he like uploaded it like on Sunday, so that's why I did it for today. But he did, like, I looked to see if it was for today, but there's no due dates and stuff. So like, yeah,
I'm just gonna do them all and bring them
yeah.
probably Friday or something.
Mhm. Yeah, so I guess, I'll just wait, like,
Until
if
they
he
ask.
says something,
Yeah.
because we can just say he didn't like
Well,
put a, yeah, tell us or put a due date, because he, like, he put the homework, but he didn't say due date, so. Like, at the end, yeah.
it's all right. Should we pack up or what?
Right? Is it, this Bible one for this week?
I think it's due for next week because we didn't have, one for today for this week. I think it's due next week.
Okay. Have about 1 minute left, so I can do one more thing before you go. Go on. You guys have a class after this?
Yeah.
Huh?
I do.
Is it around here or you have to walk a far distance?
The one over
Okay. I'll just do it quick then. So, what would be what would be its acceleration at time equals 5?
for that one?
Yeah.
Well, first you gotta get the,
It's fine, but-
What do I do to it?
do you need to first take that one?
What do I do with it?
The-
Yes. The prime of t, which is equal to your acceleration, is 2t. So what is the acceleration at time equals 5?
Yeah.
Huh?
10.
10. 10 what?
Nanometers or with second?
Squared.
Yeah, that was the thing. I know there was something like squared or something.
Seconds squared. Yes.
And so for the other one, what are the units that you're?
Nanometers per second. Position was in nanometers. Velocity is nanometers per second squared.
For the jerk, which ones are they?
What would be the jerk?
Yeah, if we like the units.
Nanometers per second cubed.
Cubed, and it would be two, yeah.
Yeah, the jerk would be 2.
Mhm.
It'd be 2 nanometers per second cubed. Okay, I think that's a good stopping spot. Let's see here. We didn't get to related rates, but we can get more into that later on. So then we have, yeah, I will do my best to upload these before Wednesday, video lectures. And then, yeah, all the way up to 2.9 will be on the chapter 2 test. And I'm gonna probably make it an online test. So on Thursday, you guys can have lab off to study. If you have any questions and I'm not around, feel free to email or something like that. Okay, good job.
Thank you.
No problem.